Okay, this is quiz 8.2 on gas laws. So let's look at question 1. A weather balloon starts in Cedar City with a pressure, and I'm going to label these as P1, T1, V1, because these are our initial conditions. So P1 is equal to 0.82 atmospheres. T1 is equal to 21.5 degrees Celsius. I'm going to go ahead and convert that to Kelvin because we know that Kelvin is what we need for the gas laws. So that 21.5 degrees Celsius is 294.65 Kelvin. And then the V1 is equal to 18.75 liters. And our first question, sorry. The first question is just going to ask for the number of moles of gas in the balloon. And so we're going to use the ideal gas law, PV is equal to nRT. We'll rearrange that to say that N is equal to PV over RT. And so N here is going to equal 0.82 atmospheres times 18.75 liters over, and R can take on different values and units depending on its context. In this case we want 0.08206 liters atmospheres per mole Kelvin. And I'll put that in, and and the temperature times the temperature of 294.65 Kelvin. And we put that in the calculator and we're going to get 0.636 moles. With only 2 sig figs, that would be 0.64 moles to the proper number of significant figures. The next question says, if the balloon is filled with helium gas, find the mass of the gas inside the balloon. Well, we know that we have 0.636 moles, and if it's filled with helium gas, then that is moles of helium atoms. And looking on the periodic table, we can see that the atomic weight of helium is 4.003 grams for every 1 mole. And that gives us 2.54 grams, or 2.5 grams with only the 2 sig figs. To find the density, and usually densities of substances are in units of grams per cubic centimeter. We'll want to first convert this volume into a cubic centimeter. A cubic centimeter is the same as a milliliter, so every liter is just 1,000 cubic centimeters. That means we have 18,750 cubic centimeters. And so the density of the balloon is going to be the mass divided by its volume. That would be 2.54 grams divided by 18,750 cubic centimeters. And that ends up being 1.4 times 10 to the negative 4th. grams per cubic centimeter. And as a reference, water is about 1 gram per cubic centimeter. Metals can be several grams, up to like 20 grams per cubic centimeter for some of the heaviest metals. And so helium gas has a very low density compared to those things. And then to find the density for the surrounding air, we're going to recognize, first of all, that whatever volume that is taken up by the helium balloon, it would be taken up, excuse me, if it were filled with nitrogen instead, it would have the exact same number of moles. Nothing about PV equals nRT is specific to the identity of the gas that you're talking about. And so if we were to find the density of the air around us, it might be easiest to just use these same numbers and assume that the balloon is filled with nitrogen. And so I really only need to change a couple of things. I'll go ahead and change them on the blackboard right here. Okay, oop, I should change that as well. So if I have 0.636 moles of nitrogen gas is N2, then it would have, oh, you know what? I've done this wrong on my, notes here. So let me really quickly solve it correctly. I'll show you how I do that. All right. So it's going to be 0.636, well, let's do this first. 14.007 grams per mole is the atomic weight of nitrogen. What I forgot to do is multiply it by 2. So it's 28.014 grams per mole. Okay, and then we'll say 28.014 grams per mole times that 0.636 moles, and that's going to be 17.82 grams of nitrogen. We'll put the 17.82 grams of nitrogen divided by the 18,750 cubic centimeters. So that'll be 17.816904 divided by 18,750, and that's going to be 9.5 times 10 to the negative 4. (9.5 times 10 to the negative 4th grams per cubic centimeter. And I apologize that I had to do that on the fly. I worked it out ahead of time, but I made that little mistake. And so just to remind you, the helium gas density was 1.4 times 10 to the negative 4th. Nitrogen is 9.5 times 10 to the negative 4th, and so it's more than 6 times more dense than helium. Obviously that's why helium floats. Okay, now if this weather balloon is released into the upper atmosphere, and the onboard instruments, because it is a weather balloon after all, indicate pressure of 0.45 atmospheres and a temperature of negative 32.4 degrees Celsius, what will be the new volume? Let's go ahead and erase this. That lower pressure would cause the balloon to expand. The lower temperature would cause it to contract. And so those two changes are competing with each other. And without doing the math, it's anyone's guess how this will turn out. So let's do the math. What we want is P1 V1 over T1 is equal to P2 V2 over T2. And we're given P2. That is the 0.45 atmospheres. And we're given a T2. T2 was negative 32.4 degrees Celsius. If I take 273.15 and I add that negative 32.4, I can convert it to Kelvin. That's 240.75 Kelvin. And V2 is our unknown. So we can start to put values in here. 0.82 atmospheres times 18.75 liters divided by 294.65 Kelvin. That should equal our P2 of 0.45 atmospheres times V2, the unknown, divided by 240.75 Kelvin. And solving for V2 by just multiplying and dividing there, and then you multiply the 240.75 over, divide the 0.45 over, we're going to get a V2 of 28 liters. So in the end, the lower pressure wins. The balloon has expanded by about 10 liters. Okay, and finally, question 3. A car engine burns about 0.1 grams of gasoline, which is technically a mixture of different alkanes, but we'll just assume it's octane to simplify this. For each engine cycle, a car engine may have a cylinder volume of 1.25 liters, and that's like the total volume. In the car's cycle, of course, that volume can get very small as the piston compresses, but at its largest point, 1.25 liters, and operate at a temperature of about 80 degrees Celsius. If the gasoline combusts completely inside the 1.25 liter piston, what is the pressure of the combustion products? So this is a many-stage problem. We're going to be asking about the pressure of the combustion products, which means we need to know the number of moles of combustion products. And so we're going to need a balanced chemical reaction. Of course, that's an old topic, so I'll just give it to you. 2C8, H18, that is the octane, plus 25O2 is going to produce 16 CO2 plus 18 H2O. And at least within the car engine, that water will be water vapor. So that's a total of 2 moles of C8 H18, forming 34 moles of gas product. That's really the ratio that we care about. The carbon dioxide and the water combined form 34 moles of gas product. Well, there's a couple other things we need to know. The molar mass of C8 H18. That molar mass is 114.23 grams per mole. And then we'll need to know that temperature 80 degrees Celsius is 353.15 Kelvin. That's what 80 degrees Celsius is. And so this is really just a dimensional analysis problem where we're given an amount of reactant, the gasoline. We'll assume there's plenty of oxygen since it's ubiquitous in the air around us. Although a mechanic might tell you that inadequate oxygen in the engine is certainly a potential problem a car could have. But in a well-running car, there should be plenty of oxygen. And so that 0.1 gram of gasoline is our limiting reactant, and we can tell how much product is formed using that as a starting point. So 0.1 gram C8 H18, 114.23 grams of octane is 1 mole of octane, and then 2 C8 H18 is 34 moles of gas product. And this is going to give us 0.0149 moles of gas product. And now we can plug that into PV equals nRT. The pressure is going to equal nRT over the volume. And so let's put those numbers in. Our number of moles, 0.0149 moles. Gas constant is 0.08206 liters atmospheres per mole Kelvin. And the temperature of 353.15 Kelvin. All of this over that volume of 1.25 liters. And this, we only have one sig fig for the 0.1 gram, and this is going to be 0.3 atmospheres. Oh. Just the top of my head was showing there. So that is the end of quiz 8.2.